This is the second part of my 3 parts tutorial explaining how to use my free program for calculation of surface plasmon. Next, let us calculate these graphs. It's graphs about the field, penetration of field in metal, skin depth in metal, and penetration depth in dielectric. For this purpose, we need to calculate the distribution of optical field of surface plasmon across the thickness. This part calculates the distribution of optical field across the thickness. To calculate for one parameter, this one, or this one, just push Calculate Field. These two identical graphs shows the distribution across the thickness. Each graph can display different type of optical field. Is electrical or magnetic field, or each individual component along each axis, or the total field. Let us display the intensity of total field in both graphs. In the left graph, the intensity is in the linear scale. In the right graph shows the logarithm of the intensity. The negative thickness is inside of silicon. The positive thickness is inside of cobalt. We can extend the calculation window for silicon, for example, up to 500 nanometers. And recalculate field. So now from 500. Now you can see the reason why the plasmon propagation loss is substantially smaller than the propagation loss of light inside the bulk of metal. You see the plasmon propagation loss is about 2 orders of magnitude smaller than propagation loss of light in the bulk. Even these two graphs need to use different display units, decibel nanometers, decibel micrometers. The reason for such a large difference in loss is simple. As you can see, most of optical field of surface plasmon is inside dielectric, and only very little of field penetrates inside the metal. Since the absorption is proportional to the amount of light inside the metal, the plasmonic absorption is small. Also, it is possible to compare the optical field at different value of parameters, in this case at different wavelengths. Let me reduce the number of calculated points to 10. Recalculate. Next, push Calculate the field scan. It calculates the field distribution for each of these wavelengths. Now you can animate the field by pushing here. This red mark shows at which wavelength the field is shown. Also, it is possible to display all graphs simultaneously. Just go to the 800 wavelengths, as most left wavelengths, and let's reduce number of displayed graphs to 10. So next, when you push, so you see, you display how the field distribution change for each of these wavelengths. Let's reduce again to 1. Let us return back to the calculation of these graphs, which shows the skin depth, penetration depth in dielectric, and percentage of the field inside of metal as function of wavelengths. For a single wavelength, those parameters are already calculated here. This part is the left part. Calculate those parameters for the scan. Choose here what kind of field parameters you would like to calculate. Let's state percentage of light in the metal and push calculate. Yeah, you can just rescal. Next, just copy and paste. Yeah, this is for cobalt. Let's choose another metal. For example, gold. Let's keep 100. So gold. We can calculate. It's important to recalculate scan and recalculate field scan. So now we can calculate. This is for gold. So that we recalculated this graph. Next, I will recalculate these figures for plasmonic structure, which contains two layers of dielectric, silicon and silicon dioxide. For this purpose, let us change this lower dielectric part. So we need to input as layer number 0 silicon dioxide and as layer number 1 silicon. So let's go to for inputting part, increase number of layer to 2, and for example let's choose silicon dioxide from formula. It is silicon dioxide. Let's input like thickness 10 nanometers, and we put it as a 0 layer, the first 0 layer, without repetition. So we have silicon dioxide here, and as for silicon, let's take it from file. So silicon is here. We choose silicon. We can just compare refractive index of both. So now silicon, yeah, we put again some, it just last layers of 500 will be 500 nanometers will be fine. But now this is layer number 1. You see, you can number 1. No, again, no repetition. Set layer, so silicon dioxide, next silicon. Push set layer. So you see we have silicon dioxide as 0 layer and silicon as number 1. Since silicon dioxide layer is very thin, let us use as suggested propagation constant the refractive index of silicon. So last layer of dielectric, silicon. So that is a silicon. We can reduce even more the thickness of silicon dioxide in order to minimize its influence. Next, push calculate. All okay. So now we're going to scan the thickness of silicon dioxide layer. So let's use we scan thickness. we scan this part, not metal part, dielectric part, and we scan zero layer, so that is a zero with no repetition. And since we're going to approach the cutoff, let's increase number of calculated point in order to approach to cutoff with smaller steps. Let's scan the thickness from 1 nanometer to 30 nanometer, thickness of silicon dioxide. We're making 40. And we can, so it started from 1 using this constant, and next we'll go to 40 using, always using previous data for suggested value. Calculate scan. So you see, we ask for calculation till 40, but it's calculated only till 5 nanometers. It is because for the structure, plasmon exists only up to 5 nanometer thickness. In case of thicker silicon dioxide layer, plasmon are not supported because there's no use calculating to 40 reduced to 6 with this 100 points, so it will be more points and we can more precisely reach the cutoff value. Yeah, you see? You can see that near cutoff thickness of 5 nanometers, the propagation loss of surface plasmon approaches zero value. This is magic of this method. I would like to repeat it once again. The major problem of any plasmonic device is the propagation loss. This problem can be completely resolved if one designs a very specific and very optimized structure which contains 2 or more dielectric layers with very specific and optimized thicknesses. Let's just copy this data, which is for gold. And calculate same data for chromium, for example. Just from file, chromium. Let's again just not use layer number 0. Again, let's calculate first for small silicon dioxide thickness. So no problem here. And let's scan little bit for thicker film, 25. So you see now the cutoff thickness is about 9 nanometers, so let's increase precision so it will be more dense, more dots for this 100 dots. Yes, so we got about cutoff thickness about 9 nanometers. So let's copy this data and plot it. Let's change to logarithmic scale. Yeah, so we got the same graph as here. You can see that every metal has its own optimum silicon dioxide thickness, at which the plasmonic loss becomes very small. There is a misconception that there are plasmon-friendly metals like gold, aluminum, and copper, in which the absorption of light is weakest, and the only which should be chosen for use in plasmonic devices. And there are plasmon-unfriendly metals like cobalt, iron, chromium, in which light absorption is much stronger and which should not be used in plasmonic devices. If we look at data of simple single-dielectric plasmonic structure, it is true. The propagation loss of gold, aluminum and copper is indeed smaller. However, take a look at this two-dielectric optimized structure. The fact is that the plasmon propagation loss can be optimized to be near zero in any of these metals. It is important finding because now we can use a metal for plasmonic device based on its property, like magneto-optical effect. We are not limited to a few magical metals, which are supposed to be only one, to be able to provide a small plasmonic loss. I will continue to explain how to use the program in the third part. Please continue to the third part. There is a link in the description below.